Alright, you're here to learn about transport networks or flow networks. So a transport network mathematically is a directed graph that has three main components. First main component is the source. So the source is a node with a 0 in degree, which means that there is nothing going into the node, there's only things going out of the node. This is our origin place of our flow. So if we are doing something with water pipes, then we're probably starting the water at node number 1. The second main component is the sink. So the sink is the opposite of the source. It has an out degree of 0 and its in degree is non-negative, so everything ends up at the sink. So this would be the very end of our pipeline. So these are the two main components. The third one is our edges. So these are our directed edges. They have a head and a tail, and they each have something called a capacity. So this is how much of whatever we're putting through can be handled by that edge. So let's say we have some water in node 1, and we have, say, 4 units of water. Then we can only put 3 up into node 2 here, and the remaining 1 has to go to 3 because we have 4 units we have to get through, and this one edge here can't hold all of our water, so we have to distribute it to other edges. So this is a transport network. So what is a flow? Well, a flow is essentially a function that assigns each edge a non-negative number. We'll call this Fij for flow, and it doesn't exceed the capacity, which is Cij. So C for capacity, F for flow. Now remember what I said before is we can have, say, a 3 here. So we can say, okay, this pipe is wide enough for 3 units of water to get through. So this is our Cij. And we can say how much flow is going through. So in this case, maybe we only have 2 units of water that we have to push through our pipes. So we can label this edge as 3, 2, which means it has a capacity of 3, but its flow is only 2. So this is what we mean when we say flow. So we can have a whole graph of these pairs with capacities and flows, and we can see where all the water is going to. So we have this other principle called the conservation of flow. Now what this says is that if you have 5 units going into a node, you should have 5 units going out of a node. So for instance, let's say we have 5 going in, then we should have, say, a 3 and 2, or a 4 and 1, or a 0 and 5. But there shouldn't be more going into a node than it can release, because otherwise we get this blockage, and that's really bad for the flow and mathematically not allowed. So what is a nice result of this conservation of flow? Well, that means that if we start a flow at our source, it should be the same amount as the sink. So if we have 7 units in our source, we should have 7 units in our sink after it travels through. Now, of course, our capacities here are 3 and 2, so there's no way we could get 7 out of our source to begin with, so the most we could get is 5 here, which means that our sink should have 5 units at the end, if possible. Okay, so now that we know about our definitions here, the main idea, we should talk about maximum flows. Okay, so this is the main problem here. We have a bunch of pipes, and we want to get the most water through our pipes as possible. So here I have this little diagram here. Remember, our ordered pairs are going to have its capacity and then its flow. So we have a source node we'll call 1, and a sink node we'll call 4, and we'll just label these 2 and 3. And we see from 1 to 4, it has a capacity of 6, and the whole flow is 6. So we're getting 6 units from 1 to 4. Here's the question, can we do better? Can we make this push out even more water? And what's the maximum amount of water we can push through this network? Well, this one's pretty easy to see because I put these numbers out, but we can see that there's 4 units we can push from 1 to 3, and 4 units we can push from 3 to 4. So we can have a whole total of 4 going from our sink to from our source to our sink. And if we go from 1 to 2, we could push 8, but at this 2 to 4, we can only fit 6. So we should probably maximize this 6 and say, okay, well, we can only get 6 to 2 and 6 from 2 to 4, so let's just put 6 in there. So now we have 6 going through that direction, so the best we can do here is getting 10 from our source to 10 in our sink. So this original path with just 6 was kind of bad, but we can do better. We could do 10. So that is the problem here. How, taking a graph with more than 4 nodes and more paths, can we get the maximum flow possible? Well, like all of graph theory, there are algorithms. So this is the Edmonds Karp algorithm that I'll be talking about today. It is similar to Dijkstra's algorithm in a sense. Dijkstra's algorithm was meant to minimize the amount of distance between all of the nodes in a tree, and in this one we want to maximize the amount of flow we can get out of a directed graph. So when I say similar, really I mean not really, so it's not really similar. But if you've seen the Dijkstra's algorithm video, the labeling and the method we use here is going to seem much, much simpler, so I'd suggest checking that out, but I'll still go through at a nice pace for this one. So what's the method? Well, our objective is to maximize flow, so our method should maximize flow somehow. Okay, so we're going to maximize flow along a path. So we're going to use up a bunch of our nodes, we're going to create a path through our system, and we're going to use as much as we possibly can. Then once we've got to the end, we're going to backtrack, and we're going to say, okay, well, we fit this amount of units through our pipes, so let's pretend that all of those capacities have been used up, and we'll just repeat the cycle until we can no longer get from our source to our sink. So, seems a little bit difficult at first, might be a little bit hard to wrap your mind around, but we'll do the mathematics and we'll do the example. So, here is our first round. So this algorithm goes in several rounds. We go through the graph multiple times, and you'll see I've sort of changed the notation up. So what I've done here is I've split all of our edges up into 2 directions. So for instance, E12 means the amount of flow we have available from 1 to 2 is 3, and the amount of flow we have going backwards is 0. So I'm going to label this as capacity, and this is going to be what we've used. So we've used 0 flow out of it. This is like our tracker, because we want to track to see how much we've used every single time. So this screen is going to get a little bit messy, but we'll go by this step by step. So first, we start with our source node, and we label it N0 for our first set of nodes. And in this first set, we say, okay, where can we get to? And we can get to 2, and we can get to 3. So what we do is we move to one of these nodes, so let's say we move to 2, and we ask ourselves, okay, how much can we get out of it? Well, we have a capacity of 3, so we can get 3 out of our second node. So this first edge from 1 to 2, we can get 3 out of it. And where does it come from? It comes from the first node. So we label it as 3, 1. And this is the amount of flow, that's the 3, and the 1 is where we came from. Okay, so where else could we get from the first node? We could get 2, 3. So how much can we get out of 3? Well, let's look at the edge 1, 3. We have 2 available. So we can write this as, okay, we have 2 available, and it's coming from 1. Okay, so those are all the nodes that we could reach from 1. So now what we're going to do is we're going to say, okay, if we could get to a node from N0, we're going to label it as N1. So this is our N1 set of nodes, is 2 and 3. So now we'll start with the smallest number, 2. So where can 2 go? 2 can go to 4. So from 2, how much can we get out of it? Well, we say that we have a capacity of 4, so we could get 4 out of it, but we have only 3 available at this point. because we could only get 3 from 1. So the most we can get from the edge 2 to 4 is 3. So we're going to put a 3 in there. Okay. And can we get 2 anywhere else? Well, we can get to 3, but we've already been to 3, so we'll just ignore it. This is a little bit different from Dijkstra's algorithm where we'd say, wait a second, if we can do better, then we're going to replace it. But in this algorithm, we're not going to do that because we're looking to exhaust our pipes. We're not looking to distribute our flow. We're looking to go down a path and say, shove as much as we possibly can into it. And then once that's exhausted, we'll go try another route and we'll keep shoving water as much as we possibly can through these pipes. So we're not going to go over this old node. So now we've done 2, let's move on to 3. So where can 3 go that nowhere else has been? Well, it can get to 6. It can get to our sink node. So it comes from 3, and how much can we get out of it? Well, we can get up to 6, but we only have 2, so we can get 2. Okay. So it is done when the sink node is labeled. So I know you're saying, hold on a second, why not this guy? And the answer is, well, we'll deal with him later. But for now, we've gotten to our sink node, so we'll do the backtracking step. So what does this graph tell us so far? Well, we have a path here. From 6, we went from 3, because we got 2 from 3. From 3, we got 2 from the first node. So we have this path right here. And this is the path we took. So we got 2 out of this whole path. We got 2 units of whatever we're pushing through out of this path 1, 3, and 6. So what we'll do is we'll say, okay, let's pretend from now on that we have 2 units of water already rushing through here. So we're just going to pretend it's always used up and not consider it for the next cycles. So what we do is we subtract 2 from all of the edges we've used, and then we're going to add 2 for how much we've used. So this is just our mental track here. So for 1, 3, we have 0 space left, and we've used 2 space. And for our edge 3, 6, we have a total of 6 available, but we've already used 2 of them. So we'll just have 4 remaining, and now we've used 2. So this was the first round. We have now updated our edges, we've backtracked through, and we've reserved our flow. So now we just start over again. So as you can see here, I've updated the numbers, just cleaned it up a bit by making these slides in advance. So now when we consider things, we start back at the source node, and we try to get back to the sink. So we can do the same thing. Okay, from 1 to 2, we can get 3 out of it, and it comes from 1. But what about this case now? What about 1 to 3? Well, we can't get to 3 anymore because there's no capacity left. So we just leave it as blank and we say, okay, we can't get to 3 from 1, so let's just not label it. So again, this is our N0. So now this becomes our N1 here. So where does 2 go? Well, 2 goes to 4. So just like before, we have a capacity of 4 here, but we can only get 3 out of it. So the most we can get is 3, and that comes from 2. But now when we take a look at 3 here, we can get to 3 from 2. And how much can we get out of it? Well, it has a capacity of 2 here, so we can get 2 out of it from 2. Because we have 3 already, but we can't fit more than 3 through the pipe, we can only fit 2, so we can say, okay, the most we can get from this edge 2 to 3 is just 2. So that's all 2 could reach, so now these are our N2s. Okay, so again, we start with our lowest number, and let's see where we can go. 3 goes to 6. It has 2 right now. It has a capacity of 4 between 3 and 6, so we can get 2 out of it, and it comes from 3. And now our sink has been labeled, so we are done. So let's backtrack. Where did we come from? Well, we got 2 from 3, and then we got 2 from 2, and then we got 3 from 1. Okay, but as you can see here, we had to ditch all 3. We had to just take 2. But really what matters is that we take the minimum amount. So here we can see we got 2 in our 3 to 6. We got 2 from our 2 to 3. So we're just going to subtract 2 from all of our flows. So this had a capacity of 4, but now we're using 2 more of it. So it ends up as 2. And we've used 2 more, so it was 6. So now it's 2 plus 2 is 4. So that's saying we used 4 out of the 6 capacity for this 3-6 edge. Then we went from 2 to 3 and we took 2 from it. So now there's no more capacity available in this 2 to 3 node. So it's 0 and 2. And we used 2 from 1 to 2. So even though we have 3 written up here, we didn't use all 3, we just used 2 of it, because only 2 made it to the sync node. So we just subtract 2 from our first, and we add 2 to say, okay, well, we've used 2 here. So that was the second round. So now when we update our numbers here, this is what we have left. So as you can see here, we only have 2 remaining from our edge from 3 to 6, and we only have 1 remaining from our edge 1 to 2. So this should be the final bout because, as you can see here, we only have 1 capacity remaining and 0 capacity remaining for our 1 to 3 edge. So let's see what we can do. We start with our source node. We move up to number 2 and we say, okay, we can get 1 unit from the first node. And that's it. So we can't get to this third node here from 1. Okay, so what about from 2? Well, from 2, we can go to 4. We can get 1 out of it. It has a capacity of 4, but we only have 1 flow we can use, so we can get 1 out of it, and that comes from 2. What about to 3? Well, we can't go to 3 anymore because this has no capacity. These 2 lines are now cut off. So we can't go that way. We can only go to 4. What about now? So we go from 4. Well, we can go from 4 to 3 because there's 2 capacity here. So we can say, okay, I can get 1 unit from 4. And then from 5, I can also go there. So I can get 1 unit from 4, and I can go to 5 because we have a capacity of 3. Okay, so now you could go from 5 to 6 or 3 to 6. But if you remember the algorithm, we always use the lowest number. So we're going to go from 3 to 6. And we can get 1 out of it because it still has a capacity of 2, and that comes from 3. So we've labeled the sync node, so now we are done. So let's backtrack and update some of our numbers here. So we've got a total of 1 flow from 3, so that's -1 plus 1. So we now have 1 capacity remaining in our 3-6 edge, and we've used 5. So we got 1 from 4, so we should subtract 1 and add 1 here. So that means that we've now only have 1 capacity remaining from this 4-3 edge, and we've used 1. We got 1 from 2, so this thing that had 4 capacity here now only has 3, and we've used 1. And of course I accidentally erased that line, okay. And now from 2, we get 1 flow from 1. So now we have exhausted our 1-2 edge. Okay, so let's update some numbers here. Did I misadd? That should be 3. So 2 plus 1 is 3. Okay, I can add. I'm good at math. Sometimes. I pretend I am. Okay, so round 4. We know we're done when we can no longer reach the sync node from the source. So can we go from 1 to 6? Well, we can't go to 2 because there's no capacity left, and we can't go to 3 because there's no capacity left. So we are done. These are the final numbers. So you're saying, okay, well, how do I draw a flow graph from this? Well, if you remember from before, we label our edges with capacities and flows. So what I'm going to do first is I'm going to label all the edges with how much flow we've used. So we have a 3 flow from 1 to 2. We have a 2 flow from 1 to 3. Again, I'm just looking at these numbers at the bottom here. So these are how much we used. If we take a look at these numbers that I'm circling. So we can label these edges. So it's 3, 2. 2 to 3 is using 2. 2 to 4 is using 1. 4 to 5 is using 1. 5 to 6 is using 1. 4 to 3 is using 0. And 3 to 6 is using 4. I just realized now that in this example, I went from 5 to 6 instead of 3 to 6. So as you can see here, my numbers, they are a little bit off, but it does not matter which one you use. As long as you pick one. For this demonstration, I just picked the lowest number, but I guess when I made the slides earlier, I used 5 instead. So either way works. We'll just say that we use the flow from 5 to 6. But what we could do is we could change these numbers if we want. 5, 0, and they would be the same thing because that's how I did it in the example. But for the sake of this, let's just update it and say it's 4, 1. But they are the same. Okay, so that is our flow. So this is pretty much done. You could say this is the flow between the networks. Let's check our things here. We have 5 leaving the source, and we have 5 entering the sink. So we're good. We have a source, we have a sink, and the out degree of the source is equal to the in degree of the sink. Therefore, our flow network must be good. So we can summarize this, and we can put this in its capacity flow form. So as you can see here, on the first one, it has a 3 capacity, and it's using all of its flow. Our 1 to 3 edge has 2 capacities using all of its flow, and this 3 to 6 is using 4 out of its 6 available. 5 to 6 is using 1 out of 1. 4 to 5 is using 1 out of 3. 4 to 3 is using nothing, so why do we even have this? Let's forget about that. 2 to 3 is using all 2 of it, and 2 to 4 is using 1 out of the 4 available. So we can even check each edge, and we can say, okay, well there's 3 going into it, so there must be 3 going out of it. So there's 1 going out there, and there's 2 going out there, so we're good. 1 going into here, 1 going out of there, 1 going into here, 1 going out of there, which means we have 1 coming into 6 from that side. Okay, we have 2 going from 1 to 3, and we have 2 going from 2 to 3. So that means that we should probably have 4 coming out of 3, which we do, which means 4 going into 6, and there's 5 going out of 1, so there should be 5 going into 6. Okay, so that is our final flow network. So that is the transportation network. Next video is going to be pretty short. I'll talk about cuts.